quantum mechanics is continuously throwing up new and very surprising aspects that we are just beginning to uncover.
Yeah, something wonderful about moire materials is they open new directions into discoveries that were not possible before. And one important aspect of this is topology, as recognized by several of the Nobel laureates here. That topology was introduced to understand some of the phenomena that could not be understood with the realm of quantum physics alone. And now we are introducing new probes for these materials and for these properties, and particularly combining lasers with traditional electronic transport that gives us access to properties like the Berry curvature, like the Berry connection, quantum geometry and quantum metric, that we couldn't probe otherwise. And that opens a fantastic door into the unknown, and controlling these properties may open new applications in the future as well.
If we are talking about quantum mechanics here, right, the quantum sensors of light is something that is really what advances the quantum technology these days. It's real, it's happening these days. Like if you smoke a cigarette on Burj Khalifa, right, I will be able to see it from the airport somewhere. And it's real. I can send quantum information from, again, Burj Khalifa to somewhere in Dubai, and no one is going to crack it. Actually, if you guys are interested to try, we can make such an experiment in Dubai. I think it will be fun. And going to different photon energy levels. So here, I think I've seen Brian Schmidt, right, who discovered the expansion, the acceleration of the expansion of the universe. If we search for dark matter particle candidates such as axions, right, there's a lot of interesting proposals how you can tackle it using single photon detectors in the far infrared spectrum or even in the microwave regime. So the technological advances is quite enormous, and you can do a lot of interesting things should you engineer specific sensors for specific technological needs. So that's what we're working on. And twistronics and materials based in particular on twisted Morse structures can help you to tackle some of these challenges.
The two great pillars of physics of the 20th century are quantum mechanics and Einstein's general theory of relativity. And we've heard today in wonderful talks how quantum mechanics has revolutionized technology and hence our lives, etc. And it's also important to mention that relativistic quantum field theory, which sort of is a combination of quantum mechanics and special relativity, has been tested to an unprecedented 10 to the minus 18 meters at the Large Hadron Collider in CERN. It's an amazing thing. And also, quantum field theory calculations of the magnetic moment of the electron are accurate to between experiment and theory to 11 decimal places. I mean, these are astounding what shall I say, achievements of quantum mechanics and special relativity. So the other great pillar of modern physics is general theory of relativity, which forms the framework of our understanding of the universe at large. I don't want to go into the history of all that, but today, general relativity enables us to understand black holes, because black holes are a solution of that theory. It enables us to understand cosmological spacetimes with the positive cosmological constant, as we have heard earlier in the day, which is one of the great mysteries of our times, the size of that cosmological constant. It also enables us to understand spacetimes with negative cosmological constants, which I will come to a little bit later. So these are two extremely important pillars which apply to phenomena in different realms of distances and time. But you try to put them together. That is, you try to quantize gravity just the way you successfully quantize the electromagnetic field, and you run into difficulties. And physically, perhaps it is because gravity is all attractive. I mean, there is no possibility of really getting out of the divergences that you encounter when you quantize gravity or quantize the general theory of relativity. So this is the problem. there is a problem, and one should try to tackle it. And I think there's a whole community of people who have been trying to understand how this problem can be solved. Now, gravity has been more or less forced upon us by another development of physics of the 1960s, which is called string theory. Now, I cannot explain all that very well in this very short time, but let me just say this, that if you look at scattering amplitudes for spin 2 particles which appear naturally in string theory, then you more or less have arrived at Einstein's theory of general relativity. Okay, good. But this program of trying to find a good theory, quantum theory of gravity, is embedded in some deep sense in string theory, because in string theory, by its very construction, the theory is finite in the ultraviolet. I mean, this is an incredible thing. I mean, one didn't actually order all this, but it just happened. And so there is a whole community of people called string theorists who are trying to understand this. They're trying to understand this and trying to see if there can be a unified theory of elementary particles and gravity and understand the standard model within this huge framework. All right, so string theory, besides the gravitational degrees of freedom of Einstein's theory, has new objects called branes and new objects of quantum gravity. And these objects of quantum gravity enabled us in the mid-90s, basically the work of Strominger and Waffa, to explain black hole entropy. That is, the entropy of a black hole, which is a very geometric object, can be understood as Boltzmann's formula for entropy. Okay, so that was a very significant thing, and lots of developments were there after that. And that also led to what is called holography, the ADS-CFT correspondence, and in which basically you discuss gravity in a wall. There's a box, a gravitational box, and you want to discuss gravity there, where on the boundaries of the wall is a theory which is like the theory of elementary particles or quantum field theory. And this was the great discovery of One丨February. And it is here that we find a deep connection to quantum information theory. And let me just put it this way, that in this formulation, black hole entropy is understood as von Neumann entropy, which is the central feature of information theory. It will be difficult to conceive gravity to be purely classical, because I take you back to the old Bohr-Rosenzweig argument as to why the electromagnetic field has to be quantized. I think the same arguments really apply also to gravity interacting with quantum matter, matter which is quantum. So I would think that gravity has to be quantized. But we have to discover the analog of the photons of gravity, and of course that's the great experimental challenge.
Yeah, I think it always comes as a surprise, right? And that's the beauty of quantum mechanics. These days, we still, after hundreds of years, we celebrate this year, right? We still can stumble upon something interesting and surprising. And well, Moray material is just one of the examples recently, right? Julian would confirm that, like, if you take two graphene sheets, perfectly conducting, beautiful, good metals, right? And you twist them at 1.1 degrees, suddenly it stops conducting electricity whatsoever. Because why? Just electrons decide to do so, right? Because they interact and they decide. And then if you add a little bit more electrons, they become superconducting. So it's this surprise which happens, especially in this field of, I would say, in our field, right? In the field of condensed matter physics, we stumble upon many of those things these days, yeah.
I think if we're looking for new phenomena in quantum physics, well, we're both looking at condensed matter systems, but in these systems we have new advances in terms of techniques that are able to resolve new things. We have also new materials. You were talking about the Moray materials that gives new physics, and finally we have new theory that helps us understand all these new phenomena. And it's the combination of those three things that help us move the field forward. And we don't know yet what we'll find in the future, but at least the door is open.
Well, as you probably know, like in big corporations like Google, right, they spend some time on crazy ideas. So that would be the approach we should do in science as well, which is should like 1 day per week do something absolutely useless.
I think with Dennis, we're both very grateful that institutions trust us to lead a team and to move some projects forward. And I think this should be encouraged. Encourage young people to take risks would lead to something. I think what's important is to follow your own curiosity, and if you keep being curious about what you're doing, then many people will find something, and that's the most important thing.